All right, I'm going to attempt to explain what flux density is by using rain as an analogy. So I'd like you to pretend that you went outside and you're going to keep track of the rain. First, you'd have to decide what you wanted to keep track of. So you bring your bucket outside and you could keep track of the number of drops that fall in, but that'd be really hard to count them all. The other issue with that is that the raindrops are different sizes. They have different diameters. And I made this little scale up here showing that. Anywhere from 1/100th of a millimeter up to a millimeter. So counting the drops would be hard. Plus, once they get inside here, they're just going to all mix together anyways. So it'd be better maybe just to come up with an amount of overall water. So let's say that you decide to just look at the overall volume of water in liters, for example. All right, another thing you would want to keep track of is the time that you were out there for, because if you were out there for longer, you would collect more rain. If you're out there for shorter, you would collect less rain. So what you could do is you could take your overall amount of water collected and just divide it by the amount of time you were out there. So let's say you collected 8 liters of water every 2 hours. Well, that would end up being about 4 liters every 1 hour if you divided those two. So that would be really helpful for you to keep track of that. Another thing you want to keep track of is the opening of your bucket and how much area this occupied, because the wider this bucket and the bigger this area, the more rain that would fall into it. So you'd want to know how big of an area you were catching rain over. And so, like the time, you could just divide by the area of the opening to keep track of how much rain you were getting in liters per how much time per amount of area. And then finally, if you wanted to get really fancy, you could also keep track of the drop sizes you were allowing in. So I'd like you to pretend that you had some fancy filter here. And this filter somehow allowed you to only allow into your bucket certain drops of rain, certain size drops of rain. So if we come up here and look at our drop size range, for example, if your filter let in these drops and wouldn't let in any of these, then you'd only get water from these guys, right? But if you let in all of these, well, then you're going to be getting more rain in your bucket. So the range of drop sizes is important in terms of reporting out what you actually collected in your bucket. So like the other things, like time and area of the opening, we could just divide by the range of drop sizes that you allowed in. You can think of these as windows, right? You had a window of time over which you collected rain. You had a window of area over which you were looking. Well, you also have a window of drop sizes over which you're allowing into your bucket. So let's say that coming back up to this, you let in drops from, I don't know, here to here. So let's say this was 0.11 millimeters, and so I just subtract these two to find the range of drop sizes to be 0.1 millimeters. And so let's pretend that was my range. And so this is how much water I collected for every 2 hours over an area of 2 square meters over a drop size range of 1/10 of a millimeter. And if I do the math here, 8 over 2 is 4, over 2 is 2, over 0.1 gives me 20 liters for every 1 hour, for every 1 square meter of area, for every 1 millimeter of drop size. Could also write that like this: 20 liters per hour meter squared millimeter. All right, so let's compare that to catching light drops from a star. So a light drop, aka a photon, will be falling into our bucket. This would be like our telescope. And this time, instead of different drop sizes, photons don't really have like a width like this. I just drew this, I drew them like this so that you kind of get an idea that there are different photons. Photons have a property called frequency, and they also have a property called wavelength, and they also carry energy. So I decided that I'm going to give these photons a frequency range up here. You can see that up here. So when you're here trying to collect the light from this star, again, it'd be hard to actually just count individual photons that are falling into our bucket. So one thing that you could do is you could just keep track of the overall energy that entered your bucket. Because once it gets in here, the detector is not really going to distinguish between, different photons. It's going to collect all of that light and add it all up into one big jumble. So we're going to keep track of how much overall energy was entered our bucket. Again, we also want to keep track of how much time we collected the light for, because the longer I collect light for, the more light I'm going to collect. Again, we want to know what this area is for this opening, because if this is a bigger area, then I'm going to collect more light. If it's a smaller area, I'll collect less light. And then this time, instead of range of drop sizes, we're going to use a range of frequencies. And so we're going to pretend that we have some filter here that only lets in certain frequencies of light. So, like I said before, if I have a filter and it only lets in these guys, or this range from here to here, then I'm only going to get I'm only going to get energy from those photons. But if I have a filter that lets in all of these, well, then I'm going to get more overall energy in my bucket. And so it's important to keep track of the range of frequencies that I use. You can think of these again as windows. This is a window of time. This is a window of area over which I looked, and this is a window of frequencies that I allowed into my bucket. So here's an example. Let's say I collected 10 joules over the course of 4 seconds over an area of half a meter squared, and this is my frequency range, and I just kind of randomly chose these numbers. So if I do the math here, 10 divided by 4 is 2.5, divided by half is 5, and divided by 1 times 10 to the 8th, so that would be 5 times 10 to the minus 8th joules for every 1 second of collection, for every 1 square meter I had as an area opening, for every 1 hertz of frequency range. Or I could write that like this: 5 times 10 to the minus 8th joules per second meters squared hertz. And this quantity is called the flux density. And basically what it is, it's how much energy you've collected per amount of time that you collected that energy for, over a certain area that you collected that energy, over a certain window of frequencies over which you collected the energy. Another thing I could do is just use a different unit for this. So there's a unit for flux density called the Janskys, named after a guy named Janskys, and I know that that is 1 times 10 to the minus 26 joules per second meters squared hertz for every 1 Janskys, JY. And so if I do the math here, I get 5 times 10 to the 18th, and my units cancel out, and I'm left with this. So 5 times 10 to the 18th Janskys. So this is what a Janskys is, and this is what flux density is.